Okay, this is solid liquid extraction, or otherwise known simply as leaching. So by definition, when we speak of leaching, it refers to the extraction of a soluble constituent from a solid by means of a solvent. So this is contrary to everything that you have studied so far, from heat and mass transfer to the other separation processes that you have learned. This one takes out a soluble component from a solid matrix. In here, we still need a solvent in the form of a liquid. Another way of looking at it is it's the soluble material that is being dissolved from its mixture with an inert solid by means of a liquid solvent. Now this time in the definition, the word inert was already used because it's very important that our carrier solvent for our soluble constituent is inert to the solvent, meaning the solvent will preferentially only take out or absorb or dissolve that particular soluble constituent, but it should remain inert to the carrier solid or the matrix in which our soluble constituent is being, shall I say, merged with or intertwined with. Now, there's another term that is used for leaching, specifically if the solvent that is used is water, and that is simply referred to as washing. So when the solvent is pure water and we take out a solid from a solid matrix, then that is also known as washing. Now, what's the principle of operation? So the first thing is there has to be contact. There has to be contact with the solid and the solvent. The solid that is carried by an inert solid matrix, or that is in an inert solid matrix. The second is the solvent separates the soluble constituent from the inert solid matrix. And then last is from the, shall we say, from the extracted form or the solvent that has already taken out the solid from the solid matrix, from the inner solid matrix, there's a need for prior, or rather there's a need for further, not prior, further separation process in the form of liquid-liquid extraction, this time to separate the dissolved solid in the solvent and the solvent. That way the solvent can be regenerated if there's a need for it to be regenerated. Now, in most industrial practices, after leaching class, there is what we call liquid-liquid extraction. Of course, with the aid that the solvent that was used in taking out the soluble constituent in the inert solid matrix could be reused or could be regenerated. So that's the purpose of extraction. So the next step always after leaching is the extraction of the dissolved solid from the solvent that took it out from the solid matrix. Okay, so this is what I have explained already. So solvent interaction with the solid, separate desired substance from the solid matrix using the solvent and extract desired substance for collection. Now, the principle of operation still, it could be performed in batch, semi-batch, or continuous fashion, referring to leaching, and may be operated at an elevated temperature. Some is operating it for at an elevated temperature because it aids in the process of dissolution. That is dissolution of the soluble solid in the solvent if it's at elevated temperature. Some maybe has something to do with bioleaching. It's a new thing now that is being used, and that will be presented to you in the form of a video in the next slides. Then flow is essentially cross current or counter current. So it could be counter current or it could be cross current. Now, another thing is that the amount of soluble material removed is often greater than in ordinary filtration washing. And the properties of the solid may change considerably during the leaching operation, meaning as to the behavior of the solid as leaching progresses, its behavior becomes, shall we say, dynamic, ever changing throughout the leaching process. Now, what are the important factors that we need to consider in leaching? Of course, very important is the size. So it has something to do with particle size. Why is particle size important? It's because we want to increase as much as possible the amount of surface area exposed to the solvent. The greater the value of the surface area exposed, the greater is the mass transfer. So we want as much as possible to have our solid, where our soluble constituent is mixed with, should be in the smallest possible size. Now, we need also to look into the solvent, not only as to the price, not only to the availability, but the recoverability of the solvent. Or can the solvent be recovered? Can it be regenerated for further use? So those are things that we need to look into. Then temperature. So it was already mentioned that in some leaching processes, the temperature is elevated, not only to increase the solution, but also to enhance the way the bacteria will act on the mineral waste, which you will learn later in the case of bioleaching. And then in some leaching operations, actually not some, but the majority of the leaching operations, if it's in the tank form, or if the leaching process is inside the tank and in series of what we call thickeners, we have what we call agitation. This is to ensure that the solvent gets to contact as much as possible the greater amount of the surface area of the solid. Now, the three factors that aid in leaching is temperature. They are also factors to consider in leaching: the contact time in the area and the solvent selection. So when we speak of temperature, temperature is adjusted to optimize solubility and mass transfer. When you speak of contact time and area, so liquid to solid contact is essential for the extraction to take place, and in maximizing contact area per unit volume, reducing equipment size requirement. So the greater the amount of contacted area will reduce the requirement for equipment size. Now, in the case of those thickeners, because there is leaching which we call heap leaching. Now, solvent selection. So solvent selection plays an important role also in solubilities, as well as the separation steps that follow leaching. So I have mentioned that after leaching, we still have liquid-liquid extraction. So nearly all leaching equipment employs some type of agitation to aid in mass transfer and to ensure proper mixing. Now, process overview. So in a typical leaching operation, this is now the way it's presented, by the way, in Giancouplisse and in McCabe. The solid mixture to be separated consists of particles, inert insoluble carrier B and solute A. So solute A is the one that we're interested in. The inert insoluble solid carrier B is the one that we're not interested in. So it is shall I say, inert towards the solvent. And it's referred to as inert because the solvent should not, of course, dissolve it together with A. Otherwise, it defeats the objective of having to separate A from B. Now, another component, C. So this is how it's represented in unit operations books. So the solvent is represented as C, and it is being added to the mixture to selectively dissolve A. Now, we have two terms here. We have the overflow and the underflow. So the overflow from the stage is free of solids and consists only of solvent C and dissolved A. So take note, the overflow is free of solids. It does not contain any solids and consists only of the solvent and the solute A. The underflow consists of the slurry of liquid of similar composition in the liquid overflow and the inert insoluble solid carrier B. So our underflow contains liquid and the inert insoluble solid B. So that is why it's called a slurry. The concentration of the liquid in the underflow is similar to the concentration of the overflow, which does not contain any solid. In an ideal leaching equilibrium stage, it is assumed that all the solute A is dissolved by the solvent C, and none of the inert insoluble solid carrier B is dissolved. We will continue. Now, the mass ratio of the solid to liquid in the underflow is dependent on the type of the equipment that is being used and the property of the two phases. Now, leaching is essentially countercurrent in most cases, and in industrial leaching, solvent and solid are mixed, allowed to approach equilibrium, and the two phases then are separated. The solvent phase, equivalent to the extract phase in liquid-liquid extraction, is called the overflow. It becomes more concentrated as it contacts in stage-wise fashion the increasingly solvent-rich solid. Now the underflow, equivalent to the raffinate in liquid-liquid extraction, becomes less concentrated in soluble material as it moves toward the fresh solvent phase. So it's a given that your underflow becomes leaner in A and your overflow becomes more concentrated in A as they proceed along in the process. Now, there are two categories of leaching equipment. So we have what we call percolation leaching, or in this case, it is the liquid that is added to the solids. So the solvent is contacted with the solid in a continuous or batch method. So this is popular for extreme amounts of solids to be processed, and that's percolation. The solvent is being percolated through the solids. Now, in dispersed solids, the solid is added to the liquid solvent. So it's being dispersed. So we know then that when we speak of dispersion, it has only something to do with either liquid or gas phases. Now, you've learned here that solids could also be dispersed in liquid. Now, the solids are usually crushed into small pieces before being contacted with the solvent. This is popular leaching method with an especially high recovery rate can economically justify the typically higher operating cost. So the operating cost here in this process, in this type of leaching is high. This is usually employed in gold extraction. However, it has high recovery. So the high recovery compensates for the economical, extra economical requirement that the process requires. So if you are to take note, something that is unique between these two methods or categories of leaching, percolation is essentially used when there is a large amount of solid to be processed. If high recovery is the thing, then you are to use dispersed solid leaching. Now, as to the equipment, so these equipments that you will be able to see in this slide are the equipments that you'll be able to read from John Kuplis and McCabe. And together with the things available in the two books that we have, I also included from Colson, because if you're going to read what is in John Kuplis and in McCabe on the topic of bleaching, it's not substantial. If you're going to ask me, it's very short. The discussion is very short, and in the case of John Kuplis, it's more focused on graphical approach. Whereas if we use Colson, the volume of Colson that discusses leaching, the approach is more on analytical, meaning it makes use of empirical equations in solving problems or in processing problems concerning leaching. But going back to the equipment, so we have fixed bed leaching, we have moving bed leaching, and we have dispersed bed leaching. So these are the different types of equipments. Now in fixed bed leaching, so we have here, in this case, of course, the bed of solids is not moving. That is why it's called fixed bed leaching. This is often used in the beet sugar industry. Sugar beets are being processed placed inside a particular equipment, and then the solvent is being percolated through the sugar beets. In the process, the solvent carries with it or dissolves the sugar from the beets. So this is also used for extraction of tanning extracts from tan barks. So extract from tan barks and extraction of pharmaceuticals from barks of trees and even seeds. Okay, so fixed bed leaching. The equipment is not moving. The solid is placed inside the equipment. Now, what about moving bed leaching? So we have different types of equipments that uses moving bed principle. And the one that is found in Jan Kuplis and in McCabe is Bollman extraction or Bullman extractor, specifically for the equipment. And we have the Hildebrandt extractor also. So for the Bullman extractor, so I have placed here two illustrations. Both are illustration of the Bullman extractor. So you have buckets that are moving. So it's the bed of solids that is being moved, and the liquid is being percolated through the solids inside the bucket. So you have spray here. This spray is of course your solvent, and you have the solids here being reloaded on an emptied bucket. The bucket that is already exhausted is its content is being turned over in here in this particular receptacle. The solid or spent solids already. Since it's already emptied, it is being refilled by this particular equipment here that places the solid inside, and again you have the liquid solvent that is being sprayed on it. This is our Bullman extractor in different views. So it's an enclosed moving bed bucket elevator device where there are perforations in the bottom of each bucket. So the perforations allow the extracted solute by the solvent to pass through and being collected. Now the Hildebrandt extractor uses screws or moving screws, consists of 3 screw conveyors. If this one is bucket elevator, this one is screw conveyors arranged in a U shape. So U shape, this is another portion of that particular extractor, and solvent flows counter currently. Okay, still your solids is moving because it's the screw conveyor that is moving the solid, and the solvent is being trickled through the moving solids by that is carried through in the movement of your screws. So this is your Hildebrandt extractor. You can read both of these types of extractors in your books in unit operations. Now, we also have dispersed bed. So this is what I've been referring to a while ago, and the use of thickeners. We call them thickeners because they are already series of leaching equipments. So we call them already thickeners. So you have the fresh solids being introduced here, and you have the fresh solvent being introduced here. So the process is counter current. So the solvent that carries a portion of the solute leached out from the solid is introduced here and then further in here. Now you have the solid that is being withdrawn at the bottom. So this is your extracted solid pump here on the last. The concentrated solution is being withdrawn here. Your feed solids is introduced in this part. So the flow is still counter current. We refer to this entire system as a thickener, or series of counter current thickeners. So the mode of extracting, or rather the mode of leaching, is dispersed bed leaching. It is the solid that is being introduced into the equipment which has the solvent. Now, what about the industrial application of leaching, or its industrial applications? So in food processing, this one is beet, where sugar is extracted from. In pharmaceutical industry, specifically in the extraction of essential oils or oils from plants, and even in the processing of, shall I say, expensive, shall I say, drug, in which there's a need for some solid raw material to be dispersed through a particular equipment which has the solvent. Before, we are fortunate, that was probably around 15 years ago or 20 years ago, that we can still go to pharmaceutical industries and we get to see how the drugs that we are buying in the drugstores are being processed. Okay, now, so we have to content with what we have now. And in here, the most commonly, shall I say, this is the commonly known application of leaching that's in the metal processing industry. From the initial phase of taking the ore from the ground up to the last portion in which the, shall we say, the waste mineral ore is being processed, it's all having the process of leaching. Okay, now, so from sugar beets to sugar. Then vegetable oil from nuts, and beans, and seeds using organic solvents such as hexane. So that's leaching because we're taking out our solute from the solid matrix. Then we have extraction of gold from ore. Now, if we process metals straight from the ore that is mined, the process is normally known as high pressure acid leaching, or we call it the HPAL process. Our Palawan, shall we say, CBNC, Palawan Coral Bay Nickel Corporation, is processing, actually, it's not mining straight from the ground, the nickel, but rather the waste material out of the processing of the ore processes. So the plant, the CBNC, processes the waste material out of processing an ore. The goal is to get the nickel from the waste ore. So it's not really raw ore, but already the waste ore. The process of taking out nickel from that particular waste ore is what we call as high pressure acid leaching. So high pressure, it's using acid to leach out nickel. Okay, we are also able to, fortunate also that we're able to have our industry immersion in this particular benefactor of USLS. Okay, now this is then the way they process the old way of processing waste mineral ores through high pressure acid leaching, depending on the acid that is being used. But most of the time, the acid that is being used is sulfuric acid. Okay, now there is this what we call bioleaching. Bioleaching, the end product is still metals, precious metals from, take note of, from waste materials, product of processing the original raw mined ore. Okay, what is this bioleaching? So I want you to listen to this. This is just short. So this is the process of producing copper cathode, okay, using heap leaching. But as to the actual process of bioleaching, it's being explained here.
We consume an increasing amount of minerals in everyday life, but mineral resources are not inexhaustible. When we extract metals from underground deposits, Many are left behind, as the remaining elements are not valuable enough to extract. This is known as mineral processing waste. To extract valuable metals from mineral processing waste, scientists began to study a natural phenomenon: bioleaching. Let's see how it works. Mineral processing waste contains minerals, but also living bacteria.
We bacteria can thrive in these piles of waste. All we need is access to air and water to multiply. But we also need energy, which we can collect by dissolving and transforming metals. This is bioleaching. In the process, we release acids that can pollute soils and cause environmental damage. To scale this process up for our needs, the scientists came up with a process to boost our metal production. To do this, the mineral matter we live in is ground into a powder and plunged into a bioreactor, a large and continuously stirred tank with water and nutrients. In this environment, we can thrive and multiply exponentially. The result is a solution that contains the metals originally contained in the mining waste. Then, all that's left to do is chemically filter the solution to retrieve the metals in solid form. This process also has the benefit of keeping the sulfuric acid we produce within the lab or factory. Otherwise, it may leach into the soil. The bioleaching process has moved beyond research and is now applied in the field. Bioleaching produces 5% of all gold and 20 to 25% of all copper extracted today. And research is still underway to find methods of applying this process to other waste, such as circuit boards, for example. In this manner, scientists have found new methods that protect the environment and reduce waste by extracting the most value from it.
So in here, we have learned that waste materials from processed ores can actually be processed again using bioleaching. Of course, it entails a lot of money. But what is money in exchange for sustainable growth and sustainable development? So I have noticed that most mining companies are simply, shall I say, storing, I like to say, use the term storing their waste in excavated grounds or mountains, and they will place their waste there. And then they will brag about the trees being able to grow in such pile of waste or in those mountain of waste, let's say 10 years after they have done their own research on how to make those particular land area habitable by living organisms such as, of course, trees that we need. Bioleaching is really very, shall I say, beneficial in the sense that it separates the acid from the metal. So aside from recovering the expensive metals, it's also able to recover the acid. And still, there are still researches ongoing about bioleaching and how it can be made use in ensuring that, of course, Mother Earth is being protected from further harm. Okay, now we move on. So now let's go to the actual thing of, let's say, having to process problems concerning leaching and when is equilibrium attained in leaching. Now, solvent forms a liquid solution. We know that in leaching, and carrier may be totally immiscible. The carrier solid, that is, may be totally immiscible in this solution made of the solvent or comprising of the solvent and the solute A. Now, some solution, however, is normally retained by the solid and has the same composition as the liquid. And we have discussed this. This solution that has already the solid is what we call as the underflow. When the amount of retained solution is constant, meaning when the solid in the underflow, which is already in slurry form, retains a constant amount of solution, then we have what we call a constant solution underflow. There are problems that gives you a constant underflow scenario, but there are problems also that gives you variable underflow scenario. And the two has to be really distinguished or discriminated. Now, when we speak of variable underflow, of course, it's the opposite of the constant solution underflow. This exists when the amount of retained solution is a function of concentration. Most of the time, class, the amount of solution that is retained in the slurry with the solid is really dependent on the concentration of the solution. So the amount of solution is dependent on the concentration of that same solution as well. So if that particular amount is constant, then there is not much great variability to oversee during the entire leaching operation. But if there is variable underflow, of course, again, your equilibrium curve will be a curve. Whereas if it's a constant solution underflow, your relationship between these two will be that of a line because it's constant. Now, how do we number stages in the case of counter current thickeners? So stages are numbered by flow direction of the solid. Wherever is the solid introduced, that is your stage 1. So which part of the process is your solid being introduced, that's your stage number 1. So you start counting off from that particular part of your process. Then what are the very important assumptions that you need to never forget regarding leaching? So the solute-free solid is insoluble in the solvent. That's overly emphasized already. And the flow rate of the solid is constant through the cascade. This is very important. This is a very important principle when we do calculations concerning leaching. Why? Because your inert insoluble solid is constant all throughout the process. So whatever is the value of your inert insoluble solid, as your solid is introduced in your process, that is the same amount of inert insoluble solid that will be carried all throughout to your series of thickeners. So flow rate of solid is constant through the cascade. A solid, of course, needs to be porous and inert to the solvent. And the amount of solution retained by the solid in the slurry phase is dependent on the concentration. So it was mentioned it is dependent on the concentration. Why? Because it's dependent on the density and the viscosity of that same liquid. The amount of solution retained by the solid in the slurry phase is dependent on the density and viscosity of the liquid, which is in which the solid is suspended, which is in turn dependent on the concentration. So bottom line, the amounts of solution retained rather is dependent on the concentration. The concentration is dependent on density and viscosity. Now, solvent amount is sufficient to dissolve all the solute. So we assume that all the solute in the solid is leached out by the solvent. That's also an assumption. And there is no adsorption of the solute on the solid. Take note, no adsorption. So your solute will not get adsorbed on the surface of your inert insoluble solid B. Solution in the liquid phase, which is the overflow, is the same solution that remain in the solid matrix in the settled slurry, which is the underflow. Now, if we have single stage leaching class, so this is how we label things with leaching. So your slurry is labeled as LO as it enters, or this is actually your original solid that needs to be processed. And it leaves your single stage extractor as L1, or your leaching equipment. So it was just referred to in here as extractor. What is NO? So NO is the amount of inert insoluble solid B. Now, what is very unique about the process of leaching if compared to the other unit separation processes is this. We are so used of labeling concentration in the solvent or in the gas phase as Y. But in here, we label the concentration of the solvent as X. So the V here, which is referred to as the solvent, V1, V2, the amount of solvent, the fresh solvent that is introduced into your leaching equipment. V1 is already your solute-rich solvent, okay? Or this is your overflow already. Both having concentrations X1 and X2, which is supposed to be Y, based on what we have learned, what you have learned in the past. But in the case of leaching, we label it as X. So the one that is going with the L phases, referring to the concentration, will now be the Y. So nagsuli-ay ang X and Y representation sa leaching. Okay. By the way, the NO and the N1 are solid content but in the form of concentration. But if only amount, if we're only asked for the amount of the inert insoluble solid, that would simply be B. But in terms of concentration, that would be the N. So we label the streams in the same way that we label the streams in other separation processes. So this is 0 because this is still to be processed. Your slurry is to be understood to be the feed that has the solid, or your feed solid specifically. So then it will enter stage 1. So this, it must be coming from stage 0. Okay, now moving on. So this is it. I've mentioned it already. N is the concentration of the inert insoluble solid B in the slurry phase and even in your feed. The concentration of the inert solid in the feed is also represented by N. Now, another thing, so what's unique about leaching is that there's an interchange in the representation of concentration. So X for the solvent and Y for the feed and the underflow. Another one is when we express concentration here, class, we don't take into account the inert solid. We only take into account A and C, the solute and the solvent. So take note here, when we express concentration of the inert insoluble solid B in the slurry or in the feed, the denominator only consists of the amount of A and C. It did not take into account the B. It's the same, this same thing is also true with the other phases in leaching. It's always only over kilogram A and kilogram C. It does not account B. So take note for this example, the composition of A in the overflow. This is already the solvent that carries with it the solute. So XA, so take note X, not Y. XA is kilogram A over kilogram A plus kilogram C. It's understood that it will not have the B here because we don't have solids in the overflow. But in the case of the underflow, the liquid in the slurry, you have kilogram A over kilogram A plus kilogram C, contrary to the way we used to express concentration as having a denominator consisting of the sum of all the components. So in here, our slurry contains already B, but in the denominator, you don't account for the B. It's only kilogram A plus kilogram C. And take note again, you're using Y, not X. So this is how we express concentration in leaching. It's in the form of, shall I say, you cannot say it fraction, but it's not also pure mass ratio. It's just kilogram of the solute over the kilogram of the solute and the solvent, not taking into account B. For the feed, so you have N to be kilogram B over kilogram A, especially in most cases wherein the feed does not contain the solvent itself. And of course, we don't have the solvent. So YA in the feed is equal to 1.0. So your A over A, so that would be 1.0 because you don't have a plus kilogram C in the denominator. In the case of the entering solvent, you don't have solids on it, so N is 0. It follows since N is 0, no, it doesn't have to do with this, but rather your XA is also 0. In most cases, class, your solvent only has the C on it. No initial amount of the solute to be leached out is present in the solvent. So we don't have A, so and as such, we have XA being equal to 0. So look, solvent is X, feed is Y in terms of representation. Now, this problem that I'm going to share with you the solution of, that would be next week. is a problem taken from Colson. So you won't be able to see this in Genku Please. I have problems coming from Colson and I have some from Genku Please, but the ones from Genku Please is really relying heavily on graphical approach. Though I understand that there's still a need to know how the graphical technique is being used. So we will discuss this Monday next week because of course this week is your week. Our week by the way, so we can also recharge. Okay? Do you have any questions for now? So what we'll be discussing next week will be the sample problems on leaching. Leaching is a short topic. Then probably the following week we'll go to adsorption. Last is membrane separation, I think. We only have 3 topics for enter. Any question? No question. I have already placed this in Canvas a few minutes ago before the start of the class. I will just place in there instructions on the next topics, or I will place the next topic so that you will have an idea on what to read concerning the next topics, especially in unit operations. So if there aren't any questions, we'll call it a day. Stop recording.